Welcome to our fourth and final class for LED programming with Arduino and FastLED at HackadayU. We've learned a ton so far about how to program using FastLED, but this class we're going to take our LED programming skills to the next level by exploring advanced patterns and behaviors for our LED matrix. Up until now, we've been demonstrating lighting patterns using the Circuit Playground Express's onboard LEDs. But if you go back, you can apply any pattern we've created to use our matrix by adjusting the number of LEDs and adjusting the data pin to be the pin we've connected our matrix to. That said, the pattern might not always fill the matrix the way we'd expect. Because LEDs on matrices can be wired either in series or in parallel, and might be snaked or not snaked, it'll change how the lights are output to our matrix and what kind of pattern that displays. In this class, we'll specifically explore patterns designed to work with our matrix. We'll explore complex noise and generative patterns, as well as how to create patterns from images to make our own pixel art. We'll explore how to get our lighting effects to work with sound input in a more advanced way to create a sound spectralizer. We'll conclude by discussing how we might use what we've learned so far about LED products and power supplies in an installation, and some considerations when working with LEDs in exhibitions. We've got a ton to cover before we can call this class a wrap, so let's jump in. If you haven't already set up your matrix, open the file Color Palette Matrix. Upload the sketch to your microcontroller and then unplug your microcontroller. Make sure that everything is off before you attempt the following. If you have set up your matrix already, feel free to jump to the next section.
Hey, so I'm Cathy and I'm going to show you how to connect your LED matrix. Okay, so the first thing to do, make sure your power supply is set to 5 volts. As you can see, mine's set to 5 volts. And then make sure it's off, make sure the circuit playground isn't plugged in, everything's disconnected, and we're ready to start. So the first thing you need is a black alligator clip. And we're going to we need to connect all the grounds here, so we're going to connect it to ground on the circuit playground. There we go. And we're going to connect it to both of the grounds on the matrix. So this one in the middle, and this one on the first part, the data in for the matrix. And I kind of like to just hold them together like this. And put this guy on here, make sure it hits them both pretty good. And then you want to connect that to the ground on the power supply, and I usually just kind of chomp it on, in this case, just like that. Then slide these down to cover it, and make sure he's out of the way. You don't ever want this to touch the power, or your matrix will have a bad day. And then the next step is get a yellow or blue or green alligator clip. We're going to connect the data line, connect pin A1 on the circuit playground, and I've got my little resistor here, so just connect it like so. And if you have trouble with the resistor, it is perfectly fine to skip it. It's best practice, but these will work without it. So you've got that. You're going to connect that to the data in on this left side of the matrix. Then once you get that, the last step is to connect the power from the power supply to this 5 volt pin on the middle of the matrix, like so. And yeah, at that point, that's the 3 connections. You've got 3 grounds. The one from the circuit playground and 2 on the matrix are tied to ground on the power supply. You've got power on your matrix connected to power on the power supply. And you've got pin A1 run into data in on the matrix. Cool, so now we're ready to turn it on. I'm going to go upload code and come on back. Okay, and here we are. I've uploaded code and I'm ready to turn this on. The first thing we're going to do is power up the power supply. It's no big deal this time because we're not powering anything off the board, but if you are, you really want your power supply on first, so that there'll be enough power for whatever lights you have plugged in. If you have too many lights plugged in, like running them off the board without like external power, it's very easy to make your Arduino freeze up because it can't power itself. So we're going to turn the power supply on first, turn it on or plug it in. And then we're very carefully going to plug in our microcontroller, just like this. Boop. And there you have it, it lights up. Yeah, make sure nothing shorts. You always want to keep ground and power like a good way away. Don't let those two touch. It's a bad idea. But anyway, yeah, this is a little bit washed out, but you can see our lovely patterns. And this file is on GitHub for you. It's called Color Palette Matrix. So yeah, check that out, and thanks for coming.
If you've got your example sketch loaded, double-check all your connections, making sure that power and ground are not in contact with each other. If all's well, plug in the power supply and then your circuit playground, and you should see the matrix light up with our test pattern. If you don't see that, stop immediately, unplug the circuit playground and then the power supply, and recheck your connections. If things still aren't working, come to our office hours. We'll be glad to help. Once you've got everything working, it's time to start developing code for our 16 by 16 matrix. But before we start, I'd like to note that it's extremely important to keep the power draw low when working with the NeoPixel matrix. I've set the brightness on all our examples to 64 to help do this. As Adafruit's site points out, quote, "Don't forget, with 256 LEDs, you could use over 15 amps of current if you turn all of the LEDs onto white, which we really do not recommend because we don't think the Plex PCB can handle that much current. Try to keep the current draw at under 5 amps. Please note, flexible PCBs are not designed for repeated flexing." End quote. Running the matrix at an excessive power draw could damage the matrix or even set it on fire, as could flexing or bending it too much. So let's keep the brightness low at all times and always try to keep your matrix flat on your desk. Got it? Right, so let's get started. From the course files, open up XY matrix. In this sketch, we'll examine one way to translate two-dimensional animations onto our one-dimensional LEDs array. First, let's look at lines 27 through 29. Here's where we're defining both our matrix width and height as 16. If we had a matrix of a different size, for example Adafruit's 8 by 32 matrix, that might look like this. Or if you have a smaller 8 by 8 matrix, you can just set both values to 8. The next line, 32, is very important. FastLED needs to know which way your matrix is wired, in a serpentine fashion, across, down, and back like a snake, or a non-serpentine fashion, from the end of each line back to the very beginning of the next, like a typewriter. Our matrix is serpentine, as are the vast majority of LED matrices, because doing it the other way involves a lot more wire. But you may see the other kind in the wild. So if you're ever trying to animate a matrix and things just aren't making sense, consider whether you might have the wrong mode set. You can always check whether a matrix is serpentine or not by animating a simple chase pattern, like our naive chase from class 2. If you watch the dot to see how it moves through the matrix, and match the movement pattern to one of the illustrations at the top of XY matrix, then set K matrix serpentine layout to true or false accordingly. Before we go further with the sketch, I want to talk a little bit about the XY coordinate system. The XY coordinate system is the way most programming languages approach the layout of the pixels on a screen. It's based on the Cartesian coordinate system you may have learned in school, although ours only uses positive numbers. It looks like this. As shown, X is the position in the row, across counting towards the right, and Y is the position in the column, down counting from the top. So combining the two describes the location of one pixel in the matrix. For instance, XY, 3, 6, means the pixel in the third row, 6th column. For more information on this, including some helpful diagrams, see here. The main part of the algorithm is on line 86. It's the XY function. XY maps an X and Y coordinate, like the ones we just discussed, to the matching index in the LED's array. Line 91 is the easy case, a non-serpentine matrix. To get the index in the LED's array, you take the Y given coordinate multiply it by the total size of the y dimension in the matrix, K matrix width, to get the total number of pixels described by the y dimension, and then add the x coordinate. If you don't understand the principle, try labeling the coordinates of a small matrix on a piece of graph paper, doing the math by hand for a couple of points, and counting each pixel out with your finger. I find this helps when arrays get confusing, especially two-dimensional arrays. Lines 94 through 103 are the more difficult case, a serpentine matrix like ours. The first part, the if y and 0x01, is a somewhat neat way of checking whether y is an odd number. Odd numbers always have the bit in the binary ones place set, which is what the expression is checking for. Y and 0x01 says, take the bitwise and of y and 1, which is true if any of the same bits are set in both the number 1, which only has the one bit set, and y. So the only way it can be true is if the ones place bit is set in y, which means it must be an odd number. Every odd number can be expressed as some even number, which we're not even examining, plus 1. For more on this frankly way too complicated thing to put in an example, see here. Anyway, long story short, just trust me that this line means, is y odd? If so, odd rows run backwards. So we're doing the same y times k matrix width calculation as before, and then adding the reverse position for x. Otherwise, we're just going to take y times k matrix width and add x like earlier, since xy wasn't on an odd row. Whew! So that's how you calculate where in your LED's matrix your coordinates are. Fortunately, you can just cut and paste this function and use it forever without having to explain it, which makes you luckier than me. But before we move on, let's take heed of the note given in the comment above xy. As we discussed before, writing to a position beyond the end of our array or before it can cause unpredictable effects, and certainly won't animate your lights. Check to make sure your coordinates always fall between 0 and k matrix width or k matrix height when using this function. The next function you'll see down on line 155, xySafe. xySafe is a clever way around this problem. As described in the extensive comment, this declares an extra pixel in our array and then moves the pointer for the array up one element. We haven't gotten into pointers, but they are a more advanced C construct that allows you to point to a special variable called a pointer to the location in memory of another variable. And that's what the star in CRGB star equals portion of line 153 means. This line creates a new pointer to a CRGB object and points it to LEDs plus safety pixel plus 1, or LEDs plus safety pixel 1. Then the magic is on lines 157 and 158. If x or y are beyond the size of the array, the function returns -1. LEDs -1 would normally be nonsense and would cause you to write beyond the bounds of your array. But since we've moved the whole array pointer up 1, LEDs -1 just points to LEDs plus safety pixel 0. That position is safe to write to, and it never gets drawn either, because we never pass LEDs plus safety pixel to FastLED show. In short, xySafe is a function you can use that ensures you can't write past the end of your array, which can be surprisingly easy to do when writing code, especially for arrays which aren't square. I don't tend to use it. I prefer to do my own error checking, or I just design my for loops, calls to random, and other LED assignments so that they don't overwrite. But you can use it elsewhere if you'd like. Just make sure to copy lines 152 and lines 153 with it. Because if you try to use this function with an array you've defined normally, like the CRGB LEDs k matrix width times k matrix height, chances are you'll write past it. After all this, our draw one frame and loop functions are pretty simple. Draw one frame smears pretty shifting bars of color across the whole matrix, giving a starting hue. In our loop function, the starting hue is based on time, and 2 deltas to add to the color for each step through x and y. In our loop function, these are calculated based on two slightly different cosine waves. It's the cosines that drive the movement of the color bars. Upload this sketch and check out what it does. Congratulations, you've just worked through your first matrix programming example. Open up the sketch Noise plus Palette. In this sketch, we'll learn to generate Perlin simplex noise across an LED matrix. Ken Perlin is a programmer who originated many of the algorithms we use to generate what's called gradient noise, ever-shifting patterns which are used as textures in games, CGI, and other forms of computer art. Simplex noise, which we'll be examining here, is a later improvement on this original algorithm, but both are often colloquially referred to as Perlin noise. Fun fact, Perlin invented his first noise algorithm for one of my favorite all-time movies, Tron. Anyway, the cool thing about noise is that it can be used to mimic the ordered randomness we see in nature. Waves, clouds, fire, smoke, lava, islands, whole continents, random 1960s movie computer processing blips, and many other fascinating effects can be generated with 2D noise in ways that never repeat. For more on Perlin and his algorithms, see the following resources. The algorithm itself is so complicated that FastLED has implemented it in a convenient function for you. We'll be learning how to use the inNoise8 function to fill a two-dimensional array with noise values, and then we'll learn how to translate the noise to colors from our color palettes and display it. As a warning, please note that some of the noise values in the sketch can create strobing or flashing effects, which may affect you if you have photosensitive epilepsy or other photosensitivities. If so, you may wish to skip uploading this sketch at the end of the section. The first thing we should discuss in this sketch is on line 39. Here you'll see a define statement for max dimension, and then you'll see some parameters. The question mark here, and the subsequent colon, is a less common way of writing a one-line if statement in C. What this line says is, if K-matrix width is greater than height, then define max dimension as K-matrix width. Otherwise, define it as K-matrix height. The formula is basically this. We won't need to worry about this in our case because both matrix dimensions are the same, but I wanted to point it out because it might be confusing if you've never seen this before. Next, we've got our LED array, as normal, and a set of x, y, z coordinates used to generate noise for every position in our noise array. We'll be setting these to random locations inside setup so that our noise is never the same twice. The next interesting things are our speed and scale variables. You can see these annotated for you. These are the primary controllable parameters for our noise algorithm. Speed is kind of self-explanatory. How fast is the effect? Slow values might look more like drifting islands or clouds. High values look more like water or flickering effects. Scale, on the other hand, determines how large the contiguous area of noise are. Small values create what looks like continents or lava blobs. Large values create smaller areas of noise, until you finally end up with a crazy shifting blippy blinking effect. This sketch changes the values for speed and scale based on the current palette, which is a good way to ensure that the mood of the noise matches the colors. Once I've narrowed down the kind of effect I want, though, I personally also like to use the beats and wave functions we discussed in Class 2 to vary noise parameters slightly over time. This will give you even more variation in the way things look. Try it on your own and see what you get. On line 65, we have our noise array. It's a two-dimensional array, declared like so. As you can see, if you're using a rectangular LED matrix, the noise array will end up being a square size to match the largest dimension of the matrix. This ensures that we can colorize the noise across our whole array without repeating any area of it. We then see our definition for our palette, as always, and a color loop variable which adds a shifting base color to the palette when set to 1. Our setup happens on line 70 to 79. There's not a lot there. We have our traditional fast LED setup. And then we have X, Y, and Z set to random 16. This means we're setting our starting coordinates for the noise array using the 16-bit random function. And that brings us to fill noise 8, which actually generates our noise. The first thing you'll notice is smoothing. When running at slow speeds, the fact that we're using 8-bit noise generates artifacts, or off-looking pixels, between frames. To avoid this, if the speed is less than 50, we're computing a smoothing layer based on the speed to be used later on. Next, we're determining an X and Y position for each entry in the noise array. This is where we add the scale variable to offset the position based on how far from the noise neighbors we want to be. Note that Z doesn't change, or at least not yet. It only changes at the end of this function. Next, as commented, is some optional code to expand the value returned from iNoise from 16 to 238 back out to 0 to 255. Then if we calculated it prior, we're using our smoothing variable in an if statement. We do this by examining the last value in the position of the noise array, scaling it by our smoothing value, and then adding our new data, scaled to 256, minus the smoothing value. This minimizes abrupt changes between the two sets of data, preventing those visible artifacts we discussed earlier. You can comment out this section of the code if it's confusing too, just like the operations above, since you may not even notice the artifacts at this animation speed. Then we're setting our noise data for this location in the noise array, and then repeating for all the others, 0 through max dimension for both I and j. Lastly, we bring in our speed variable, which drives the z parameter we passed to iNoise8 earlier, as well as adding a little spice to x and y. This prevents our noise pattern from becoming too similar to itself over time, although who knows if anyone would notice it. Thus, every time you call fill noise 8, you're filling up the entire noise array using the iNoise8 function, Perlin's simplex noise algorithm, feeding it slightly different values which are based on speed and scale plus the current position in the array. The result is noise which shifts slightly every time you call the function, which is exactly what we want for generating natural seeming patterns. This is the heart of the effect used in this sketch. The rest is just using the noise to generate colors for each pixel on our matrix. In void map noise to LEDs using palette, we do exactly that, and at this point it's surprisingly simple. For each pixel, LEDs ij in the matrix, we set the brightness to be equal to the noise at noise ij, and then flip the values to noise ji to get out our color index. If we set color loop earlier, we're adding in a slowly shifting hue value so our colors don't repeat too much. Then we're brightening up the colors. If the brightness value we got from our noise is already over 127, we're pegging the brightness of the color we get back from color palette to 255. Note that this is always relative to the brightness of the entire strip, which we set inside setup earlier. Otherwise, we're using the built-in dimming function, dim8raw, to multiply the brightness by 2. We're using this because the human perception of brightness isn't always linear. What seems to us to be twice as bright is actually less than twice as bright in terms of numbers, which makes twice as bright come off as too bright. You can use this convenient function anytime you're calculating brightness differences, which seem like they're a little less or more than you need them to be. Lastly, we're grabbing the color from our palette, just like we did in our color palette sketch in class 2. And we're using the XY function, the same function we just used in the last segment, to place it in our pixel. And then we're increasing the hue in case we had color loop set. Next, we enter our loop function. The loop function is short and sweet. All we do is check whether we need to change the palette, generate our current frame's worth of noise in the noise array, call the map noise to LEDs using palette function to colorize it, and then call fastLEDShow to update the lights. After all that, this is the last thing in this sketch that isn't something we've already been through before. Again, if you're photosensitive, you may choose not to upload this sketch or watch the subsequent video. Otherwise, upload it to your Circuit Playground and see what it does. I also recommend experimenting with the speed and scale variables set for each palette inside of Change Palette and Settings periodically, so you can get a better idea of what they do. Changing these, and the color palettes of course, is the primary way you can create multiple lighting effects from your simplex noise. Noise is a go-to for me anytime I want a natural evolving effect. It's even better for this purpose than combining the waves and beats functions. You can use it to get a convincing 2D fire, water, or clouds effect, especially if you turn the speed down and just let the noise slowly evolve over time. It's not just for matrices either, since it also looks cool on the one-dimensional array of a strip. There is a 1D version of the noise function you can use for this. Simply call inNoise8x instead of inNoise8xyz. And of course you don't need to limit yourself to driving colors and brightness with noise. It can be a great driver for pixel position, animation speeds, fades, or any animation parameter that runs from 0 to 255, which in FastLED is most of them. Use the map function for the rest. As a challenge, can you change this sketch to smoothly transition between palettes rather than abruptly changing? Can you create your own palettes, including gradient palettes, and find matching noise parameters for them? Can you use the beats and wave functions discussed in Class 2 to vary the noise parameters for each animation slightly over time? Edit the code to try your hand at one or more of these challenges, and be sure to post your videos in the comments on our class page. We'd love to see what you try. In this next section, we'll learn how to source, edit, and animate classic 8-bit sprite-based characters on our NeoPixel matrix. Step 1 is to think about what sprites you might want to animate. You can use any bitmap editor, or even photo editing software like GIMP or Photoshop, to create your own sprites. Or you can head to this site, sprites-resource.com, and grab something classic. The first problem we've got is that we have a 16 by 16 matrix, and only the oldest 8-bit games, or very small details from slightly newer games, have sprites limited to 16 by 16. Old arcade games, like Galaga or Millipede, are good sources, as are some older NES and Genesis games. I wanted something from Final Fantasy, but only the Otherworld character sprites were small enough to fit in the matrix. Here's the image I've used, but I've zoomed in on it because it would look so very tiny otherwise. What you need to do is create a series of images, each of exactly 16 by 16 pixels. You can do this by trimming existing sprite sheets from Spriter's resource, or by drawing your own sprites. You can do both using any image editor. If you don't have one, I recommend using the open source photo editor GIMP, or you can Google Bitmap Editor to find tools meant for creating sprites. Your animation will look best if you fill the 16 by 16 space with your character as much as possible. Otherwise, it can be hard to keep the character's position from shifting in unwanted ways during animation. Make certain your images are exactly 16 by 16 pixels in size. Otherwise, the converted arrays will give you too many/few initializers errors when you paste them into your Arduino code. If you're on Windows, save your completed images as bitmap files, one file per frame of animation. If you're on Mac OS, save them as PNG files, one file per frame of animation. Once you have your images saved, download the open source LCD image converter on Windows or Linux, or PixelArt Sprite2 Hex for Mac OS. We'll be using one of these two programs to convert each image to an array of colors for use in our Arduino code. Once you have the converter, open up your image and select Options Conversion from the menu. Change the type to color. Go to the Image tab and change block size to 24-bit. Next, go back to the Prepare tab. Click Use Custom Script to clear the existing script from the window. Then paste the following into the code box. You can find it on GitHub in the LCD custom script text file for your convenience. This may look familiar to you. It's the serpentine rows logic from our XY function. We're using it here so we won't have to reverse any of the lines by hand or use an external program. Once you have the new code entered, you should see the scan direction animation on the right-hand side of the window change to a back and forth pattern, just the way our matrix is wired. Next, click Show Preview button in the lower left-hand corner. Select everything in the window that comes up and paste it into the curly braces, set in the frame array in your Arduino sketch. Repeat this process to convert each image in your animation. Most old sprites only have a handful of animation frames, which makes this process not too tedious. Or you can just animate our classic black mage, since I've already pasted our little mage friend into the arrays for you. Next, we'll walk through the process for Mac OS. Go to this GitHub link, and then you're going to want to select the green button for code, and then select Download Zip. Once the file's finished downloading, double-click it to unzip it, and then copy it to your desktop, or wherever else you would like to copy it to. Then copy all the PNG files you wish to convert to this directory. I also recommend keeping a separate copy of your files elsewhere in case something goes wrong. Next, open a terminal window. Navigate to the directory where you unzipped the pixel art folder. For me, that's my desktop. So I would say CD to navigate, and then I would say desktop. And now I can see that I'm working in my desktop. Then I want to CD into that file. And I'll see that I'm correctly in that file. Now type in php sprite to hex.php. If everything went right, you should have a set of beautiful Arduino arrays in your terminal window, each named after the original PNG file. From the course files, open up pixelart.eno. In the sketch pixel art, you'll see a couple options for copying and pasting your own frames. First, there's a blank frame format that you can use that has some frames laid out for you. You can add or delete frames as needed. You can also copy and paste into the existing frames. So for example, if I wanted to paste in my frog 1, I would just want to make sure that I selected all of this for frame 1, and then replaced it where I see frame 1. I'll want to continue to do this for frame 2 and for frame 3. I only have 3 frames. If you want, you can also use the classic black mage example that we already have set up. Just leave the sketch as is. Once you're done cutting and pasting, carefully count the number of frames, converted image files that you ended up with, and change the num frames defined at the top to match this number. So for my frog animation, I only have 3 frames, so I would change this to 3. If for some reason your matrix is not 16 by 16, set the matrix width and the matrix height to match the correct dimensions that you have. For example, if I had an 8 by 8 matrix, I would change it like so. At this point, I recommend verifying your sketch. You can do so using this little check mark at the top. If you get any errors, carefully check your curly bracket formatting on your array. If Arduino complains that you have too many initializers or too few initializers, your image was not exactly 16 by 16. Check to make sure that you have 16 entries in each row and 16 entries in each column of each one of your frames. I left a comment with the proper format near the top of the sketch to help you compare yours to the working one. If you get stuck, I recommend using the animation I've already converted for you. Okay, now that you've got your images converted, let's run through the algorithm. This one is just so simple, which is exactly why old games use sprite-based animations. They're one of the easiest ways to animate characters on a screen. Starting at line 10, we have our traditional LED boilerplate. We need to know how many color codes are in each frame of the animation. This is 16 by 16, or the same amount as num LEDs, 256. Then we need to know the number of frames. Update this to match your own frame numbers. If you're off, you'll either see fewer frames than you intended, or Arduino will draw one or more frames of random trash across the array at the end of your animation loop. Remember, reading beyond the bounds of an array will get you unpredictable results. Next come our animation parameters. Change light update time to your desired update speed, or keep it as is. Slow times are better for pixel animations. Note that we've added our usual lighting timer, plus a curve frame variable to help us keep track of which frame is being displayed. The setup function should look entirely familiar to you by now. Next comes display frame. It's what fills and draws our LEDs array. Check out how simple it is. All we need to do is step through the array in the given frame, setting each color straight from the hex color code that we got on our image converter. So easy! The loop function is equally simple. When our lighting timer goes off, call display frame on the current frame to fill and show our LEDs array. Increase the current frame variable by 1, resetting to 0 if we've reached the final frame. And then reset the timer for the next time. That's it! You've animated your 8-bit sprites. Upload the sketch and see what you think. If you ran into any problems getting your converted images to work, I recommend using my values. Re-download the sketch from GitHub if you need to. And you can come to our office hours or post to our class page for help. As a challenge, can you animate your sprite based on sensor input? Maybe from the accelerometer or a 4-pad cap touch controller? Show us what you come up with. Open up the sketch Mic FFT Express. In this sketch, we're going to explore an algorithm which transforms raw signal data into its constituent frequencies, called a Fourier transform. In this sketch, we'll learn to examine the sound spectrum using FFT to transform the raw sound data coming in through the built-in microphone. First, we need to install a library. To do so, go to Sketch, Include Library, and then go to Manage Libraries. In the search bar, type FFT. Select Adafruit Zero FFT library, which should be the first one that comes up. Select the most recent version and click Install. If it asks you to install additional libraries, please do so. A fast Fourier transform is an algorithm that transforms raw signal data into its constituent frequencies, or vice versa. It's especially common in music and sound recording applications, so much so that many libraries have a function to compute it for you, including ours. You can read more about it on the Wikipedia page. Now we're ready to use the sketch, and you'll see that we've included the library as one of the first lines of the sketch. The other lines in the first part of the sketch are defines and variables that will be the same every time you do spectrum analysis, unless you want to capture different frequencies or amounts of data than are shown here. The next section is an array of color values we'll use when we're visualizing the spectrum. And then there's a very short setup function, just initializing our circuit playground. Then we have a couple more variables. As you can see in the comment, this tracks low and high levels for dynamic adjustment. The whole algorithm itself is inside of our loop. But first we have to begin with capturing our data. This line, circuitplayground.mic.capture, with parentheses input data, comma data size, is what reads our raw sample data into our input data array. Everything else in the loop will transform the raw data we've already read into an array containing spectrum data, and then display it. First, we'll center our data on the average of said data. This moves outliers in the data closer to the center. Then we'll call 0FFT, input data size, to run the FFT algorithm over the input array. Next, we'll sort our data into bins. First, we're using memset to clear the existing data in the pixel data array. Memset, as you might imagine, sets memory. It's an efficient call to use when you need to clear or copy a large amount of memory, although you need to be careful with it because it's easy to overwrite things when you don't intend to. Next, we're binning our data at last. I printed min index and max index to see what was happening here, but basically the FFT algorithm has created 28 bins of its own, each with the current amplitude for the part of the spectrum. We need to translate those into 11 bins, one for each of the neopixels in our ring, plus one to hold part of the spectrum that's visually uninteresting. We accomplish this using the map function. For each index in the original bins, map the index from min-max index to 0 through num pixels. Then add the data in that index to our actual bin. That's the core of this algorithm. Bins may change, and will in the next sketch, depending on how many points of the sound spectrum you want to examine. But the technique is pretty much always the same. Take sound data, run 0FFT on it to transform it into frequencies, and then sort the frequencies into bins. Then you can print or visualize the bins to see what each part of the spectrum is doing. In the next part of the sketch, we're figuring out which value is the highest and lowest. Then we add a bonus factor if the difference is too small, otherwise the display will flicker too much. And we check the loudest and quietest sounds to see if they're louder or quieter than our max and min so far. If so, we set max level or min level to a lot, and if not, we set it to a little. Then we actually display our data. This algorithm uses 511 as the top value because it's 1 less than 2 times 255. Basically, the call to map is doubling the amplitude of the data, so that the display code can use 2 different color schemes, one for the top end of the data, colors into white, and one for the bottom end of the data, black into colors. Check out the code and see if you can work out what it's doing. Okay, let's upload the sketch and put on some music and see what it does. From your course files, open up soundspectralizer.eno. In this sketch, we'll learn to visualize sensor data across an LED matrix. We'll build a sound-reactive spectralizer, an interactive matrix lighting project. We'll need to install the FFT library. If you haven't installed it and need instructions, please see the last section, which will show you how to install this library. This sketch is a synthesis of fast LED animation code and the FFT algorithm from the last section. For the former, the main thing that changes is the number of bins. When using FFT algorithms, you need to think about how many bins you want to use. In the last case, we used only 11 bins, or the 10 pixels on the neopixel ring, plus 1 at the highest frequency to discard. In this case, we're using 17 bins, or the 16 rows in our matrix, plus 1 at the highest frequencies to discard. This way, the 16 bins we care about represent the physical layout of the matrix, which makes it easy to visualize them. This is accomplished in the define on line 26. As you can see in the comment, it says, how many bins? We want the length of the matrix because each row will be displaying one bin. I also redefined frequency min and frequency max. Because originally I wasn't getting as much movement in the center of the spectrum as I'd wanted, nor in the base frequencies. The rest of the sketch is the same as last time, although I renamed a few variables to help us understand what their purpose is, now that we're not animating across the neopixels directly. Check out the last section again and see if there's anything you don't understand. In this section, we've added our usual lighting timer and a setup function which sets up FastLED for us. And then there's just our loop. The first chunk of the loop, other than some renamed variables and the addition of our lighting timer, is exactly the same as it was in Mic FFT Express. So I'm going to skip describing it. You can go back to the next section if you need help or want more explanation. For now, let's move on to what's different in this sketch. The next big change happens where this comment is display the data. Here I'm using 3 variables to calculate an HSV color for each pixel in the matrix, assuming it has data, otherwise it'll be black. The base color is the base color for each zone. I divided the matrix in thirds. Blue for the base, purple for mid-range, red for the highs. Next, the bonus color goes up a small amount for each bin, giving them each a very slightly different hue. Last, the base hue for each column goes up by 5 for each pixel in the column, causing the colors to change near the top of the matrix when greater amounts of data are measured. You'll see this at work in the video later. Next, we're stepping through each bin with our first for loop. The first part of this code is the same as it was in Mic FFT Express, except that we're using the matrix height and the max value to map our bin data to. Here we're getting a variable, n, with the current level of this bin's spectrum data in it. We're also calculating the base color for this bin or column, depending on how far through the width of the array it is. The first third of the matrix is the base frequencies, and I liked blue for those. I chose purple for the next third, the mid-range, and red for the last third. Then to calculate the actual color for each pixel, I'm stepping through from 0 to n, the current level for this bin we got earlier, increasing base hue a little each time. Then to calculate the actual color for each pixel, I'm stepping through 0 to n, the current level for this bin we got earlier, increasing base hue a little each time, and then adding base color, bonus color, and base hue to get a final hue value for each pixel. I load this into the array for each, and then step back over the rest of the column, from n to matrix height, to set the rest of the pixels to black. This ensures that old data won't just linger on the display. And that's it! The 4 loops, one for every bin and then one for each pixel in the column corresponding to the bin, have colorized every pixel in the array. All we need to do now is call FastLED show and update our timer for next time. Lastly, I pasted the XY routine from XY matrix into the bottom of the file so we can use it inside the loop. That's it! You did it! Put on some tunes and stare at the colored lights. You can also use this online tone generator to test whether your spectrum analyzer is working properly. Turn down the volume to a comfortable level, put the slider at about 200 Hz, press play, and whip the slider slowly to the right to watch your analyzer react. You should see the bars move across the display as the tone moves. The video is upside down because that's where my computer is relative to the matrix, but you get the picture. The Circuit Playground's microphone isn't the world's best, but I think it's pretty darn good. Experiment with the frequency min and frequency max variables and music volume to dial in your Spectralizer how you want it. Now that you're a lighting programmer, let's briefly walk through the sort of planning that might go into an LED installation. When planning an LED installation, I usually start by measuring the room or object, and by thinking about what kind of effect I want. Do I want a matrix, whether purchased, pre-built, or custom soldered using sections of LED strip, serpentine style? Or do I want linear strips? And if so, top emitting or side emitting? LED neon? Maybe sealed pre-diffused pixel modules? Next, I'll look up a couple of candidates of each type. Useful sites include Adafruit, AliTuv, Super Bright LEDs, or eBay. Make sure your lights are controllable using Fast LED. Many LED strips are not RGB controllable at all, or use the DMX protocol. I recommend sticking with APA 102s or the WS281 family, but there's a convenient list of recommended protocols for Fast LED here that will update as time goes on. Once you know what lights you want to get and what area you want to add your lights to, you can start calculating how many meters or how many pixels you'll be ordering, along with how many amps it'll take to run them, and how many power injections you'll need. The datasheet for your lights should give either amps per pixel or per meter. Multiply this by your total linear distance in order to get a rough idea of how much total power the installation will draw. Then determine how many power supplies and of what size you'll need. Do this by dividing your total power draw by each power supply's rated amps, minus the rated amps, times 0.2. The latter includes your 20% overhead for safety. At this point, I like to figure out what sections of lights go on which power supply. Don't forget to allow that 20% margin, and where my power injections will be. An injection every 50 pixels is a good rule of thumb for 5-volt neopixels. Don't forget that you can also inject at the beginning and the end of the strip. A strip with 100 pixels doesn't need an injection in the middle. You can also use this calculator to get an idea of where your power draw starts to get over 15% or so. Also pay attention to the wire length on the right-hand side of the calculator. For best results, keep your power supplies as close as possible to the lights they're powering. A quick warning, it's really easy to overpower a room with RGB controllable lighting. Most home circuits have a 10 or 20 amp breaker. More than that, including everything else you may want to run off of that circuit, and you'll pop the breaker. Think about whether less is more. You may choose to run fewer feet of lighting, run the lights at a lower brightness, run fewer lit pixels in your animation, diffuse your strip or pixels so they come off as larger than they are, or combine LED lighting with lighting methods which have a larger light and color spread, like DMX, wash lights, or video projectors. Some of the coolest concert lighting installations I've seen combine video projection with a flat surface, with programmable LEDs embedded into that surface. Also note that large installations can exceed the amount of memory on the microcontroller. You can always check by changing num LEDs in an example sketch to the number of pixels you'd like to use, and then verifying the sketch. The Arduino IDE will warn you if you start to run out of memory. In my experience, anywhere up to about 90% of memory used is fine, even though Arduino starts to warn you at about 80%. If you get too close to 100%, you can experience unpredictable effects, so try not to exceed 90%. Also, don't forget that your lighting algorithm itself may take up more space than the example sketch does. If you've used too much memory, you may need multiple lighting controllers to handle your room. When I realize that I'll need more than 2 or maybe 3 microcontrollers for a single install, I like to stop and consider a control method that scales better, like Touch Designer driving a large streaming ACN controller. It may cost more, but you'll save a lot of headaches. Otherwise, you can use an army of cheap controllers and communicate via Ethernet, OSC, in order to orchestrate your animations. Ethernet messages have some inherent lag, but depending on your frame rate, it can totally work. At this point, I tend to build a spreadsheet with names, product links, and prices for all of my lights, controllers, power supplies, and any accessories I plan to buy, including wires, sensors, aluminum channel, double-sided thermal tape, zip ties, and zip tie bases, or other forms of wire strain relief. Now you've got a sheet that shows the total cost of the project and where to buy everything. From here you can buy the whole thing, but if I have time, I like to buy and build just one power supply, one controller, and a matching amount of lights, just to make sure I have all my ducks in a row. You can use this smaller rig to check your voltage draw, test interactivity, experiment with diffusion materials, prototype how you'd like to attach the lights and sensors or hide them inside objects, and test out other things, like animation looks, that are tough to try before you have lighting in hand. Once you're sure you're ready, you can buy your lighting, power supplies, and controllers, and begin building your installation. Remember to connect all ground wires within your project, including those on each microcontroller and on each power run from the supply, to prevent ground loops and other interference. We did this with our matrix, and the same principle applies for larger installs, especially if you're running more than one power supply on more than one circuit. Now you're ready to create your own interactive LED art. Let us know what you make on our class page or at our office hours. Thanks for coming. Happy hacking!